Hi, today I'm excited to talk about our recent work, Mars, an instance-aware, modular, and realistic neural simulator for autonomous driving. Our model can render photorealistic images, and thanks to the instant-aware nature of our method, we can edit the foreground objects for simulation. As you may know, autonomous driving is one of the most crucial applications of AI. We have seen great strides in the self-driving market and the capability of robotaxis, which can navigate big cities smoothly. However, a significant challenge arises when they encounter corner cases. These unexpected situations can put the lives of passengers at risk. But the conundrum we face is that while we need more training data to handle such corner cases, collecting this data in real world means dangerous and expensive. To address this challenge, the research community has turned its attention to photorealistic simulation as a promising solution. If an algorithm can experience a vast range of corner cases in a simulator that closely resemble the real world, it could potentially overcome the performance limitation of current autonomous driving systems. Let's take a look at the existing simulation method for autonomous driving. Carla, for instance, is a widely used sensor simulator that is based on the traditional graphic engine, but its realism is limited by the quality of assets. Ours, instead, train a compositional neural field based on the sensor data. And thanks to the photorealism of neural rendering pipeline, our simulator can render photorealistic photos as well as other output channels. The basic idea of neural radiance field is that all the 3D points in the space radiate light, and we can model a 3D scene with a 5-dimensional function, as shown in here, that maps the point coordinates and viewing directions to RGB colors and volume densities. Then, we can approximate the function with an implicit neural network. By performing volume rendering at a specific camera perspective, we can create realistic renderings by considering all the emitted lights from the 3D points along the ray. And the implicit neural network is then optimized using backpropagation with photometric losses. But as you may know, the original nerve can only reconstruct static scenes. To represent dynamic scenes, researchers have used deformation-based or time-conditioned dynamic nerves to solve this task. However, we observed that the most motion in autonomous driving scenes are rigid motions, and representing rigid motions with deformation or conditional dynamic nerve on time will cause huge memory consumptions and under-constrained optimization. Instead, we propose to use compositional neural representations that separately model each component in the scene with different neural fields and composite them together for rendering. The compositional manner also enables us to achieve modularity and editability, which our baseline method do not have. As you can see in this table, the nerve and its time-conditioned version suffer from realism, which block their application in driving simulation. Neural thin graph and panoptic neural fields are not modular, which means that they cannot easily adapt to variant nerve backbones. SUDS is unaware of the individual instances and is not able for fine-grained instance editing. To the best of our knowledge, Mars is the first open-source simulator that is both realistic, modular, and instance-aware. We show our method pipeline in this figure. We model the static background and each object in separate models. To render a pixel, we first calculate the intersection of the ray and all visible object bounding boxes. For object models, we first transform the sampled ray from the world coordinate into each object frames. Then, we query background and each foreground models individually. Our modular framework supports selecting different model architectures and samplers for each model that can best resemble the theme parts. During the forward path, each model samples an individual set of 3D points and queries their corresponding features, such as RGB colors, volume densities, and semantic logics. After merging and sorting all the samples from different models, we use standard volume rendering to obtain pixels RGB, depths and semantics, etc. Through backpropagation, our compositional network can be optimized. In the next few slides, I will delve into some of the details of our method. As we stated before, we separately model the dynamic thing with different models and allow the model to sample a set of 3D points independently. Although this enables the maximum flexibility and modularity, there might exist a bunch of sample points of the background model to be seated inside of the object bounding boxes. As you can see in this figure, the point in gray are sampled in the background model, but their location is actually occupied by the object number 1 and number 2. We call these samples the background truncated samples. As you may notice, if we let these samples involved in the compositional volume rendering, they might cause the foreground colors to be mixed in the background model. Knowing that the background truncated samples are actually in the free space of the static background, we penalize the quality of volume density of those samples so that they do not affect the final performances. Another important technique that we use is the category level object model. As is common in driving things, the majority of objects share similar appearances and shapes. Therefore, we choose to model a class of objects with a shared shape and texture network, and condition each instance with latent codes. When querying the foreground model, the texture and shape latent codes are fed into the network, along with the query point coordinates. Now, let's take a look at the pipeline again. After collecting all the sample points, we can move on to the compositional rendering process. We follow the standard volume rendering pipeline to render the pixels RGB, depths, semantics, and object RGBs, etc. For the static background, we also support using the CICAI model to deal with the appearances at infinite distance. Here we show more qualitative results on Kitty, vKitty, and their V2X dataset. And thanks to the instant awareness feature of our proposed method, we can easily manipulate the foreground objects by simply editing the object tracklets. And finally, let me show you a video demo of our method. As you can see in this video, our method photorealistically render reconstructed videos and decompose the foreground object from static background and edit the object trajectories. Thank you very much.